there, 7th graders. It's Mrs. Tremblay. We're now in section 5.4, and we're going to talk all about scale drawings. And you're going to see exactly how this relates to pretty much everything we've covered this year. It's all rolled into one. We've got proportions, simplifying fractions, measurement, all kinds of things. What I like about this section is I think most people can relate. You've seen a map, right? Maybe you've seen a blueprint to a house. And we know that these drawings are not the actual size, right? Could you imagine sitting in the car trying to read a map of Michigan that was actually the same size as Michigan? That would be crazy. So basically when we look at these maps, they give us a scale. It's a proportional relationship going on from the map to Michigan, if it's a map of Michigan. And that scale lets us know how much smaller the map actually is and how to figure out actual distances from this map, because it's not really, 3.5 centimeters from here to here. It's a lot longer. So today I want you to be able to read a map. I want you to be able to, when given a scale, find some actual measurements, because in real life you will definitely need to do that. Alright, so measurements in scale drawings and models are proportional to the measurements of the actual object. So as one doubles and triples, so does the other. The scale gives the ratio that compares the measurements of the drawing or model with the actual. So when you have a scale, it's the measurement compared to the actual distance. For example, a map might list that every inch is equal to 10 miles. So that means on the map, when you measure 1 inch, it's actually 10 miles in that 1 inch. Or you could also write it like this, as a fraction, because this and this mean the same thing. So on a map, you would probably see this one more than that one, but either one is fine. Alright, so we're going to practice finding an actual distance. If you don't have a ruler, maybe you could press pause and go grab a ruler. I have mine here, so pause. Welcome back. Okay, so here's a little map of Michigan. And let me see if you can see that. Well, I know it's on your paper. I don't have the whole thing there, but there you go. What I want you to notice is right up here, it gives us a scale. It says that 1 centimeter is equivalent to 50 miles. So if you measure 1 centimeter on this map, you actually have to travel 50 miles to get from that point to the next, or that city to the other city. Alright, so I ask you to find the actual distance between Cadillac and Detroit. And these steps right here allow you to do that. So here's Cadillac, here's Detroit. I'll scooch it up a little bit. Step 1 says use a ruler to find the distance on the map. Now do you see how it says 1 centimeter equals 50 miles? Please use the centimeter side of your ruler, because it doesn't say 1 inch is 50 miles, it says 1 centimeter. So from Cadillac to Detroit, you do your measurement, I'll do my measurement. Alright, it looks to me like 3.5, like 3.5. So that's my step 1, I did that. Okay, step number 2, use the scale to write a proportion. I'm going to write this 3.5 up here so I don't forget. Okay, use the scale to write a proportion. In a proportion, isn't it one fraction equals another fraction? Please say yes. Okay, so the scale here says 1 centimeters equals 50 miles. That's 1 to 50, so I'm going to write 1 over 50. And remember, this is the centimeters, this is the miles. Now we have 3.5 centimeters, right? So that 3.5 centimeters needs to go across from the centimeter. So I'm going to put my 3.5 here. And we're trying to find the actual distance, right? Wouldn't this down here be the actual distance? Because 1 centimeter is 50 miles. I want to know how many miles are in 3.5 centimeters. So I'm just going to put D here for distance. So right now, all we had to do was take one little measurement, and we can use our scale to help us solve this. We're pros at solving this by now, right? We're going to cross multiply. So D times 1 is D. And when you take 50 times 3.5, yep, it's 175. Now I definitely want to list the measurement here because I don't want there to be confusion between centimeters and the miles. So this is 175 miles. So according to this map, it's 175 miles from Cadillac to Detroit, or Detroit to Cadillac, however you look at it. All right, let's try another one. It says, what is the actual distance between Traverse City and Marquette? So on the map, find Traverse City, find Marquette. There they are. So I need to know how many centimeters it is to get from one to the other. So I'm going to put my ruler on Marquette, and I'm going to put my ruler on Traverse City. Where'd it go? There it is. Okay. So in looking at this, to me it doesn't look like it's exactly 3. It looks like it's the first dash after the 3. And since centimeters are divided up into tenths, that would make that 3 and 1/10. So 3.1. I'm going to write that right here. Step 2, so we did our measurement. Step 2, let's set up a proportion. So I'm going to use the 1 centimeter to 50 miles. And that's equivalent to, remember centimeters goes across from centimeters, 3.1 to what? We want to know what that distance is. So again, the centimeters are across from the centimeters, the miles are across from the miles. We're going to cross multiply. So D times 1 is D. And 50 times 3.1 is 155. And remember, we were finding the miles. So the distance is 155 miles. Not too bad. All right, last one I ask you, what is the actual distance between Detroit and Marquette? So let's figure out how many centimeters it is from Detroit to Marquette. Line it up. There's Detroit, there's Marquette, and when I look at mine, it looks like it's like 2 dash marks after the 7, so 7 and 2/10. So I know it's 7 and 2/10 of a centimeter. I'm now going to set up a proportion. I know that every 1 centimeter equals 50 miles. I know the distance is 7.2 centimeters, so centimeters across from centimeters. I want to know how many miles. This time I'll use M for miles. You can use any letter you want. M times 1 is M, and 50 times 7.2, that is 360 miles. So a little bit longer of a distance there. Okay, so that's reading a map. We have a few more things to do here. So turn your page. And who doesn't love a little standardized test practice? I mean, this is my hobby. I love to do standardized test practice in my spare time. I'm sure you do too. All right, so you might see a question like this, and I need you to understand that you solve this the same exact way we just did the map one. Here's the Earth. The liquid outer core of Earth is 2,300 kilometers thick. A scale model of the outer layers of Earth has a scale of 1 inch equals 500 kilometers. How thick is the liquid outer core of the model? Okay, this is just like before. I want to use the 1 to 500. So I want to solve this, and I know I'm going to use that scale of 1 inch equals 500 kilometers, right? Now this time I don't have to measure. It tells me in the problem that the liquid outer core of the Earth is 23 kilometers thick. And I'm trying to figure out how big the model one is. So you're given 2,300 kilometers. In your ratio here, the top is inches and the bottom's kilometers, right? So this time, the kilometers, those have to go on the bottom, across from the other kilometers. And I'm trying to figure out the model. So I'm going to use M for model. So I'm trying to figure out how many inches that is. And opposite of our map. We solve this the same way though. I'm going to cross multiply to make a 1 step. So instead of M being alone off the bat, I have a coefficient. It's 500M. And then 2,300 times 1 is, of course, 2,300. I'm sure you're an old pro at solving these now. All we need to do is divide by the coefficient of the variable, the number in front of the letter. And when you take 2,300 divided by 500, you end up getting, drum roll, 4.6. Now when you look up at the multiple choice options here, 4.6 happens twice, doesn't it? There's 4.6 inches and there's 4.6 kilometers. We were trying to figure out the model, right? How thick is the liquid outer core of the model? The model is measured in inches, so I'm going to select B because that's also in inches. Don't let them fool you with problems like this and just look for the 4.6. Think about what units. And if it helps, when you're solving this, put the inches and kilometers in there and put the kilometers here. And then we know, oh, we're figuring out the inches. Or use I for inches if you wanted. Whatever it takes. Do whatever it takes. All right, one more little topic here. We're going to talk about scale factor. That's not an actual spider, in case you were frightened. It's kind of freaking me out looking at it on the big screen right now, to be quite honest with you. But there we go. A scale can be written without units when the units are the same. So I could say 3 to 5 if I was talking about 3 inches to 5 inches. So when the units are exactly the same, you might not see the unit written down. A scale without units is called a scale factor. So if you want to write a scale factor, it means that your units need to be the same. This right here would not be considered a scale factor because this is inches and this is kilometers. If they were both inches or they were both kilometers, then it would be a scale factor. So you do need to understand the difference. So a scale without units is called a scale factor because the units are the same. So here's our little spider. A scale drawing of a spider is 5 centimeters long. So the drawing is 5 centimeters long. The actual spider is 10 millimeters long. So that's about a centimeter. So it's actually, not that big. It's kind of tiny. And no, spiders seem gigantic sometimes. People ask you, how big was it? And it's like, it was the size of my face. Never. They're usually pretty small in Michigan. Okay, so anyway, sorry I get off on my tangent about spiders because they freak me out. Letter A asks you what's the scale of the drawing. So if you're just telling me the scale of the drawing, this is a scale, 1 inch to 500 kilometers. We're allowed to have different units with that. So when we're trying to figure out what the scale of the drawing is, I'm going to go from the drawing to the actual. That's what you do. So drawing to actual, write that down when you're going to list a scale. It goes from the smaller one to the larger one. Okay, so in a scale I'm allowed to have 2 different units. So let's see. The drawing here is 5 centimeters, right? So 5 centimeters goes on the top. And then the actual is 10 millimeters. It says it right up there. So 10 millimeters. So right now I could say 5 centimeters to 10 millimeters, but you never want to not have a ratio simplified, right? So the GCF of 5 and 10 is 5. 5 goes into 5 once, and 5 goes into 10 twice. I have to include the units because they're different. So on a map or if a scale is listed, it's usually not listed as a fraction. It's usually listed as a ratio like this with the colon. So I would say that the scale of the drawing is 1 centimeter to 2 millimeters. All right. So now letter B, I ask you what the scale factor is, and you might be thinking, well, I already found it. It's 1 centimeter to 2 millimeters. But you remember I kind of made a big deal about saying that in a scale factor, you can not list the units because they're the same. So right now, I have 1 centimeter. I have 2 millimeters. Those are not the same. But the good news is, centimeters and millimeters, that's an easy little conversion to do. So I either need these both to be centimeters or I need them both to be millimeters. What do you think? I think it'd be a lot easier to call 1 centimeter 10 millimeters than to start using decimals within a fraction, because that's not allowed. This is 2/10 of a centimeter, right? I'd have to put a decimal point there, and you're not allowed to have decimals within ratios. So 1 centimeter actually equals 10 millimeters, right? We just talked about that on the ruler. I said this spider is 10 millimeters. Well, that's 1 centimeter. So 1 centimeter is 10 millimeters. So it's really 10 millimeters to 2 millimeters. Or 10 over 2, the GCF would be 2. So 2 goes into 10 5 times, 2 goes into 2 1 time. And now I can drop the units. I don't need to write the unit because they're both the same. So the scale factor would be 5 to 1. So hopefully we see the difference between the scale, 2 different units, it's okay, and scale factor, no units, because it means they're both the same. Let's try one more just to make sure we got this difference down. It won't take long, I promise. A sketch of a fashion designer's shirt is 9 centimeters long, because they do sketches of designs. They don't make life-size designs. The actual shirt is 1 meter long. So first I ask you, what's the scale of the drawing? Remember, it's going to go from drawing to actual. So the drawing is 9 centimeters, and the actual, it says, is 1 meter. There's not a number other than 1 that goes into both of those, so I can write this as 9 centimeters to 1 meter. Those both mean the same exact thing. So that's done, because a scale, I'm allowed to have 2 different units, right? But now I ask you in letter B what the scale factor of the drawing is. So keep in mind, we just had 9 centimeters to 1 meter, right? I need them to all be the same. So if I was trying to convert centimeters into meters, that's going to end up being a decimal. I don't want to do that. But I do know how many centimeters are in 1 meter. Do you know? I know you know. Write it down. You know it? It's 100. So there are 100 centimeters in 1 meter, and I can leave my centimeters alone up here. So do you see how I have centimeters and centimeters now? That's awesome. Is there a number that goes into 9 and 100 to simplify this thing? Nope. So when I write my scale, I'm going to write 9 colon 100, meaning the scale is 9 to 100. I can drop the units because they're the same. So you're all done. See you tomorrow.